Researchers have introduced an enhanced version of the DeepLabV3 Plus architecture, dubbed DeepLabV3++, for polyp segmentation in colonoscopy images. This model aims to improve the precision and robustness of polyp segmentation, which is crucial for the early identification and diagnosis of colorectal cancer. The proposed model incorporates efficient NetV2S within the encoder module, enabling refined feature extraction with reduced trainable parameters. Additionally, it integrates multi-scale pyramid pooling, MSPP, and parallel attention aggregation block, PAB, modules, along with a redesigned decoder, to enhance its capacity to capture multi-scale and directional features. The MSPP block incorporates diverse separable convolutional layers and attention mechanisms, enabling the model to capture intricate features and complex polyp shapes. The redesigned decoder transforms the extracted features from the encoder into a more meaningful segmentation map. The model was evaluated on 3 public datasets, achieving DICE coefficient scores of 96.20%, 96.54%, and 96.08%, respectively, outperforming several state-of-the-art models in polyp segmentation tasks. Compared to the baseline DeepLabV3 Plus model, the proposed DeepLabV3++ with its MSPP module and redesigned decoder architecture significantly reduced segmentation errors, such as false positives and negatives, across small, medium, and large polyps. This improvement in polyp delineation is crucial for accurate clinical decision-making in colonoscopy. Automated polyp segmentation in colonoscopy images can revolutionize the identification and treatment of colon cancer entirely. The proposed DeepLabV3++ model has the potential to improve the precision and robustness of polyp segmentation, ultimately leading to better clinical outcomes. DeepLabV3++, learning-based computer-aided diagnosis (CADX) system, aims to enhance the efficiency and accuracy of identifying potential polyps during colonoscopy examinations. This is achieved by integrating transformer encoder blocks, residual blocks, a pre-trained ResNet50 model, and dilated convolutions for real-time polyp segmentation. The proposed system refines the existing DeepLabV3+ architecture by introducing a novel multi-scale pyramid pooling (MSPP) module and a parallel attention aggregation block (PAB). These modifications enhance the model's ability to capture complex polyp boundaries, striking a balance between efficiency and accuracy. The MSPP module enables the model to capture multi-scale contextual information, while the PAB facilitates attention-based feature aggregation, allowing for more precise polyp boundary detection. A comprehensive comparison with other leading polyp segmentation approaches demonstrates the improved performance of DeepLabV3++. Quantitative results and qualitative examples showcase the system's ability to accurately identify polyps in real time, paving the way for enhanced colorectal cancer prevention. This section delves into the methodologies employed in deep learning models for colon polyp detection and segmentation. It commences with a discussion on CNN-based models, notably the DeepLabV3++ model, which has garnered state-of-the-art results in colon polyp segmentation tasks. The paper then proceeds to examine transformer-based models, including Transfuse, Coder, and SSFormer, which leverage the strengths of both CNNs and transformers to enhance polyp detection accuracy. Attention-based models are also scrutinized, encompassing the Guided Attention Residual Network, GARNET, and ACL-NET framework, which utilize attention mechanisms and attribute contrastive learning to improve segmentation accuracy. Lastly, the paper covers UNet-based models, such as AGCU-ResNest and Focus-UNet, which are designed to improve colorectal polyp segmentation through unique architectural designs and backbones. These models have been meticulously reviewed to provide an extensive understanding of their potential in enhancing colon polyp detection and segmentation. The DeepLabV3++ model proposes a novel architecture for accurate polyp segmentation, combining dual attention mechanisms with architectural enhancements. The model integrates the metaformer and UNet models, featuring a multi-scale upsampling block and a conviformer block. The architecture is built upon a ResNet 101 backbone, utilizing an encoder-decoder structure and incorporating an ASPP module. A key innovation of DeepLabV3++ is the introduction of multi-scale pyramid pooling with a parallel attention aggregation block, which enhances the encoder-decoder structure of DeepLabV3+. The encoder utilizes efficient NetV2S for initial feature extraction, followed by an MSPP module and POB to emphasize crucial details. This setup enables detailed feature extraction and precise polyp segmentation. The hybrid focal loss function is employed to optimize the model's performance, addressing class imbalance issues inherent in polyp segmentation tasks. Short-range skip connections are also incorporated to facilitate information flow between layers. The proposed DeepLabV3++ model offers a robust and accurate solution for polyp segmentation, leveraging the strengths of its constituent components to produce high-quality results. The DeepLabV3++ architecture presents an enhanced feature extraction technique, designed to capture multi-scale contextual information more efficiently. This is achieved through a combination of convolutional and pooling layers, each contributing uniquely to the feature extraction process. The module begins with a 5x5 separable convolution layer, followed by a 3x3 separable convolution layer and a 1x1 convolution layer, allowing for the capture of meaningful features at a larger scale without compromising computational effectiveness. A 1x1 convolution layer is used for dimension reduction and fine-grained feature extraction, preserving fine features for precise border identification. The integration of this layer into other convolutional layers improves feature fusion by merging multi-scale features, enhancing segmentation accuracy and preserving spatial characteristics. The model utilizes dilated convolutions with varying dilation rates to capture medium to large-scale context and directional information through 5x1 and 1x5 separable convolution layers, emphasizing vertical and horizontal structures. Global contextual information is gathered through average and max pooling methods. The output from these layers is then processed by the proposed POB module, which leverages attention mechanisms to suppress irrelevant information and emphasize important ones. This ensures that the model focuses on critical regions like textures and borders of polyps, producing more accurate segmentation results. DeepLabV3++ integrates spatial and channel attention mechanisms in parallel pathways to enhance feature representation. The model's architectural composition includes a parallel attention aggregation block, POB, that captures spatial relationships and channel-wise dependencies. In the first branch, spatial information is aggregated using average and max pooling operations across channels, followed by depthwise convolutions with kernel sizes of 3, 5, and 7. These outputs are concatenated and passed through a pointwise convolution to generate a 2D spatial attention map. This map encodes spatial locations to emphasize or suppress, improving the model's robustness and comprehensiveness. In the second branch, channel information is aggregated using global average pooling, GAP, and global max pooling, GMP. The combined output then passes through an MLP with two hidden layers, producing the channel attention map. The Hadamard product is used to combine the input feature with the spatial and channel attention maps, which are then added elementwise to refine the feature. This process helps the model adapt to different polyp sizes, capturing fine details in small polyps and maintaining contextual awareness in larger ones. The decoder in DeepLabV3++ refines and improves the segmentation output produced by the encoder. By combining multi-scale feature fusion, comprehensive refining, and accurate upsampling, the decoder significantly enhances the accuracy and dependability of polyp segmentation results. The encoded features are first upsampled by the decoder to bring them back to a higher resolution, necessary for thorough segmentation. The model produces a feature map corresponding to the spatial dimensions of the input image, enabling precise polyp segmentation. The decoder in DeepLabV3++ incorporates a sequence of upsampling, concatenation, and convolutional layers to efficiently combine contextual, high-level data with fine-grained features from the encoder. This process preserves precise spatial information required for successful segmentation by integrating multiscale characteristics. The concatenation phase utilizes contextual information from deeper levels of the encoder and detailed information from early layers, refining the characteristics and enhancing segmentation quality. The decoder applies a sequence of 1x1 and 3x3 convolution layers with skip connections to build more accurate borders around the segmented objects and minimize artifacts. These layers maintain fine spatial features and enhance gradient flow, facilitating deep network training. The decoder then executes an extra upsampling step to return the feature map to the initial input resolution, ensuring the size of the input image and the output segmentation map align. Finally, the decoder assembles the segmented image by mapping the upsampled features through a 3x3 convolution layer, highlighting the regions of interest in the input image. The experimental analysis section covers the utilized datasets, pre-processing steps, chosen experimental parameters, and evaluation metrics. 3 popular benchmark datasets, CVC-ColonDB, CVC-ClinicDB, and Kvasir-SEG, of colonoscopy images are used to demonstrate the capabilities of the proposed DeepLabV3++ model. The datasets are described in detail, including their resolutions, numbers of images, and annotation processes. The preprocessing and data augmentation steps involve resizing the input images to 256 by 256 and applying normalization to ensure uniform dimensions and consistent range of pixel values. Various augmentation techniques, such as horizontal and vertical flips, random rotations, and elastic transformations, are incorporated to enhance the robustness and generalization of the model. The experimental parameters include splitting the augmented dataset into training, validation, and testing sets with an 80 hours 10 minutes and 10 seconds ratio, initializing pre-trained weights, setting batch sizes, learning rates, and optimization algorithms. The proposed model comprises 8.7 million trainable parameters and is implemented with a TensorFlow backend on a Tesla P100 PCIe GPU. A hybrid loss function combining dice, binary cross-entropy loss, and boundary loss is employed to address the class imbalance problem and enhance the accuracy of segmented image boundaries. In this comprehensive study, the authors leverage DeepLabV3++, a state-of-the-art deep learning model, to tackle polyp segmentation. The research draws on 3 datasets, CVC-ColonDB, CVC-ClinicDB, and Kvasir-SEG, each with distinct characteristics and specifications outlined in tables 1 and 2. To optimize polyp segmentation, the authors employ a hybrid loss function that combines binary cross-entropy loss, dice loss, and focal loss, as defined in equation 5. This approach allows for balancing the contributions of each loss function using coefficients alpha, beta, and gamma. The focal loss, in particular, addresses class imbalance issues through the balancing factor beta k and focusing parameter gamma, as computed in equation 8. The authors evaluate the performance of their polyp segmentation model using a range of metrics, including dice coefficient, precision, recall, accuracy, and mean intersection over union, MIOU, with equations presented in equations 913. Accurate segmentation is crucial in medical imaging, and the proposed DeepLabV3++ model demonstrates exceptional performance. This is attributed to the incorporation of multi-scale pyramid pooling, MSPP, and position attention alignment blocks, POB. MSPP outperforms traditional ASPP methods by capturing features of various sizes and shapes, while POB improves segmentation precision by prioritizing important regions such as polyp boundaries and textures. The synergy of these components enables the model to achieve more accurate and consistent segmentation results than other existing state-of-the-art models. DeepLabV3++ is a novel model that outperforms existing state-of-the-art methods in polyp segmentation tasks across various datasets. It utilizes efficient NetV2S as its backbone, providing a better trade-off between accuracy and efficiency. The model incorporates a multi-scale feature pyramid network, MSFPN, module to capture contextual information at different scales, enhancing its ability to handle diverse polyp sizes and capture fine details. Compared to other state-of-the-art techniques, DeepLabV3++ consistently achieves high levels of precision and recall, demonstrating its adaptability to different polyp datasets. An ablation study was conducted to evaluate the impact of various components within the DeepLabV3++ model, confirming that the successive addition of each component contributes to improved segmentation performance. The incorporation of the MSPP module within DeepLabV3++'s encoder leads to a significant improvement in performance, achieving higher DICE and MIOU scores compared to the baseline DeepLabV3+ model. The use of the POB module inside MSPP further enhances the model's performance, leading to higher DICE scores and reduced parameters, resulting in improved inference time. The DeepLabV3++ model is a novel architecture that builds upon the existing DeepLabV3+ model by incorporating additional features. It integrates the multi-scale pyramid pooling module for refining global contextual insights and the POB module for attention focusing on important areas. This comprehensive approach leads to superior performance in polyp segmentation tasks, achieving higher accuracy, MIOU, and DICE scores compared to the baseline DeepLabV3+ model. Notably, the proposed model has a significantly smaller number of trainable parameters, which is another significant advantage. The DeepLabV3++ model, leveraging the efficient NetV2S backbone, achieves state-of-the-art performance in colonoscopy image segmentation, excelling in the accurate detection of polyp regions. Notably, it outperforms existing methods in handling complex boundary areas, shape irregularities, and unclear images. The model's efficiency is underscored by its reduced training time and computational requirements, making it a computationally lightweight solution. A comparative analysis with DeepLabV3+, as illustrated in Figure 4, reveals the DeepLabV3++ model's significant reduction in segmentation errors. This novel approach demonstrates improved robustness and accuracy in segmenting polyp areas, thereby enhancing the reliability of colonoscopy image analysis. By virtue of its exceptional performance and efficiency, the DeepLabV3++ model presents a promising tool for colonoscopy image analysis, offering a robust and accurate solution for the detection of polyp regions. The DeepLabV3++ model, as proposed, exhibits superior segmentation performance compared to existing models, particularly in diverse polyp datasets. This is achieved through the combination of multi-scale pyramid pooling, MSPP, and pyramid attention augmentation block, POB, along with the use of separable convolutions. The MSPP enhances traditional ASPP by providing comprehensive multi-scale feature extraction, while POB and separable convolutions improve segmentation accuracy while maintaining computational efficiency. In Table 4, an ablation study reveals that the proposed DeepLabV3++ model outperforms other state-of-the-art models across three benchmark public datasets of colonoscopy images: CVC-ColonDB, CVC-ClinicDB, and Kvasir-SEG. The model achieves mean intersection over union, MIOU, values of 94.74%, 95.63%, and 93.78%, as well as DICE scores of 96.20%, 96.54%, and 96.08%, respectively, for these datasets. Figure 4 illustrates the segmentation error comparison between DeepLab3+ and the proposed DeepLab3++. The highlighted area represents the XOR difference between the actual and predicted masks, indicating fewer segmentation errors in the proposed model. Future research directions include exploring advanced optimization techniques such as quantization methods and efficient architectural modifications to enhance DeepLabV3++'s efficiency. Additionally, the authors aim to expand the application of DeepLabV3++ to other medical image segmentation tasks beyond polyp segmentation. The incorporation of transformer-encoder architectures, which show promise in capturing longer-range dependencies and enhancing global context within images, is also planned for future evaluation. This research paper delves into the multifaceted aspects of colon cancer, encompassing its epidemiology, risk factors, and health services. It also delves into the role of deep learning in colonoscopy polyp segmentation, providing a comprehensive review of different neural network architectures such as UNet, DeepLabV3+, and their variants. These models have been found to be highly effective in detecting and segmenting polyps from colonoscopy images, with some achieving over 0.9 mean DICE score and 86 frames per second processing speed. The paper highlights the importance of accurate polyp detection during colonoscopy, as colon cancer is a significant global health issue, with high incidence and mortality rates. It underscores the importance of early detection and removal of polyps, which can significantly reduce the risk of colon cancer. The paper also discusses the challenges associated with polyp detection, including variability in polyp size, shape, and location, as well as the need for real-time processing to minimize procedure time and improve patient comfort. The use of deep learning models has shown promising results in addressing these challenges, offering high accuracy and speed in polyp detection. This research contributes to the ongoing efforts to improve colon cancer screening and treatment outcomes, emphasizing the potential of deep learning in enhancing the efficiency and effectiveness of colonoscopy procedures. The current page delves into the cutting-edge methods for polyp segmentation in colonoscopy images, focusing on transformer-based models that have demonstrated significant advancements in both accuracy and speed. Models such as Performer, TransUNet, and Lapformer are highlighted for their promising results, leveraging the power of transformer architectures to improve segmentation outcomes. Moreover, the page explores the utilization of attention mechanisms in models like FuzzyNet and shallow attention network, which enhance the precision of polyp detection by selectively focusing on the most relevant regions within the image. These mechanisms allow the models to better differentiate between polyps and non-polyp structures, thereby improving overall segmentation performance. In addition to transformer-based models and attention mechanisms, the page also touches upon other state-of-the-art approaches for polyp segmentation, including deep learning architectures and hybrid models. These innovative methods have been developed to tackle the challenges associated with colonoscopy image analysis, such as variability in image quality, polyp size, and location. The discussion also encompasses the importance of robust evaluation metrics for assessing the performance of these segmentation models. It emphasizes the need for comprehensive benchmarks that can accurately measure model performance across various datasets, ensuring that the developed models are reliable and effective in real-world clinical settings. Finally, the page concludes by discussing potential future directions for research in this field, including the integration of multimodal imaging techniques and the development of more efficient and interpretable models. The refinement of these segmentation methods holds great promise for enhancing the accuracy and efficiency of colon cancer screening, ultimately leading to better patient outcomes. The research paper discusses various deep learning models and techniques for colon polyp segmentation in endoscopic images. It highlights the use of transformer-based architectures, such as ColonFormer and UGCA-Net, which leverage multi-scale context and feature alignment to improve segmentation accuracy. Other state-of-the-art models like DeepLabV3++ and UNet 3+ are also applied to this task. The authors emphasize the importance of developing efficient and accurate segmentation methods, as current techniques face challenges in identifying small or flat polyps. The development of new datasets, such as Kvasir-SEG, has facilitated the evaluation and comparison of different algorithms. The paper also discusses convolutional neural networks, CNNs, and their variants, including CBAM and DOLGNEXT, which incorporate attention mechanisms and deep orthogonal fusion of local and global features to enhance performance. Additionally, the potential of multi-scale edge-guided attention networks, such as MegaNet, for weak boundary polyp segmentation is noted. The paper concludes by emphasizing the need for further research in this area, particularly in addressing the limitations of current methods and exploring novel architectures that can better handle the complexities of colonoscopy images.